Hello, and welcome back to Compressible Flow. I'm Professor Steve Miller. Today we'll have a special topic on a crash course of computational fluid dynamics. We'll look at this crash course of computational fluid dynamics, or CFD, to give you a general idea of what it is using your basic knowledge of aerodynamics, fluid dynamics, and of course compressible flow from this class. CFD, of course, aims to solve the equations of motion, whichever ones we choose, numerically. And we do that through, of course, discretization of the system of equations. The system of equations we looked at in these classes are continuum theory based. Computers, of course, are discrete because they're digital computers, and therefore we need to discretize the equations so that we can solve them with a computer, a discrete computer. CFD corresponds to 3 steps. The first step, of course, is the pre-processing phase, where we define the problem, set up the geometry, and create what we call a computational grid, which we'll show a few examples of in this class. Then, of course, the CFD itself, the solver, must solve the discretized equations with appropriate boundary conditions on the computational grid, which of course represents the fluid volume. The computational solver will find solutions, numerical solutions of the system of partial differential equations, which are discretized. The numerical error can be assessed in multiple ways. We will look for convergence, that is, the solver runs that the error in the solution decreases and becomes very small, ideally on the same order of the machine error of the computer we're running on. We also want our solutions to be stable, meaning we do not want our solvers to blow up and to say not a number, which is a common error in CFD if things are not well posed with the setup of the simulation, boundary conditions, and grid. Once our solver converges and we have a solution which is so-called independent of the grid, meaning it's grid independent, then we will look at the solution visually and assess its validity. If we believe the solution is reasonable, physical, convergent, and grid independent, then we can graph the results and do analysis to say find lift or drag or make design decisions. In fact, we're solving all the equations we found in this class with computers in computational fluid dynamics, and often the more general set of equations with appropriate boundary conditions, which of course are so far impossible to find analytical solutions of. We do not know general analytical solutions of equations of motion, and that's why we find solutions with numerical methods. Here's a general overview of CFD. CFD indeed is numerically solving an equation or sets of equations that govern a fluid motion. Throughout this crash course, we will remember the following major steps. CFD consists of 3 major steps. The pre-process, which is setting up the problem, the solver, which is solving the equations numerically, and the post-process, which is analyzing the result. We always have to balance every step and the entire process with skepticism and continually ask ourselves, is this result correct? Here's one picture from the Siemens Corporation from their manual on STAR, where they show the 3 steps. The pre-process is in 1, where they define the problem. 2 is the solver, which you see in step 2, where we find a solution. And 3 is post-processing and analyzing the results. Now, the equations of motion are almost always written as systems of partial differential equations, as we discussed in this course way back at the beginning, and they govern fluid motion. One famous system is, of course, the Navier-Stokes equations, which you should recognize below on the lower left as, of course, the continuity, momentum, and energy equation closed by an appropriate gas law. These, of course, are subject to particular boundary conditions. And we, of course, know that there's no particular analytical solutions of these equations, and therefore we must find them numerically for given boundary conditions and problems. We solve them on digital computers, and of course we have to take this set of equations and discretize it onto a computational domain. This is obviously easier stated than performed in practice, and deals with a great amount of work. Now, the systems of PDE are written in continuum fashion, and we would need to discretize them to be solved on a discrete computer. For example, each of the partial derivative terms in the system of equations in the lower left would have to be discretized onto a particular grid. Let's say we want to discretize the term partial u partial x. That's change of velocity in the x direction with respect to x. It's formally defined as a limit as delta x goes to 0 of u of x plus delta x minus ux over delta x. We can write that more compactly as this equation on the right. Say partial u of partial x at some point I will go as u of I plus 1 over minus u of I all over delta x, plus higher order terms delta x. So this is basically a very low order derivative approximation. So you see that we've rewritten our partial derivative as a change from 2 points in space, which are what we're going to call grid points, with respect to the distance between the grid points. Now, in this case, we would want to discretize all the terms in the equations with respect to time, or ignore them altogether, meaning we have a steady simulation. Now, our system will indeed be discretized, that's the partial differential equations, which can be now solved with either linear algebra solvers if it's a linear set of equations, or advanced nonlinear solvers if it's nonlinear. Of course, fluid motion is almost always governed by nonlinear equations and effects, and therefore we would have to use advanced nonlinear solvers. And therefore, what you've learned in linear algebra is not applicable to computational fluid dynamics. This is essentially what the core of the CFD program executes, the solution of the discretized set of equations on some particular grid, solving millions and millions and millions of discretized equations for a particular grid in a single flow problem. Let's look at some particular CFD codes, which can be classified in different categories. A CFD code is really a suite of computer programs that contains a visualization module, grid generation module, and a number of solvers that solve the equations. Commercial codes, which are sold to people by, say, companies, often contain everything you need and work seamlessly. They often contain a preprocessor, a solver, and a number of post-processors to visualize the results. These are often integrated into large aerospace companies' workflows into their design process and research groups. Typically, smaller groups, like our class, might use an individual CFD code, which is commercial, or perhaps we might be using a more complicated set of codes which are open source, like we are doing in the current class. You'll see by going online, there's many codes available, both for free and for pay. On the right, we show two particular screenshots from the famous CD Adapco, or now Siemens Star CCM Plus CFD software. This is taken directly from the tutorials. In the upper right, you see one of the famous problems we solved in this class. There's a wall, and the blue part is a fluid, and it's moving supersonically from left to right, and you see one particular shock wave, an expansion, and another particular shock wave. And so this is a shock expansion problem which we can solve with CFD. Thankfully, this solution also has an analytical solution, and so we can compare our CFD result with the analytical solution to see if it's correct. We also see a particular pipe flow in the preprocessor stage, just to give you an idea that you can indeed handle external or interior effects problems. Note, though, of course, that the equations of motion do not change if you're an interior flow or exterior flow. The fluid has no idea really, in reality, if it's an interior of a device or exterior. The first step of CFD, of course, is to define the problem. I believe this is the hardest part of engineering, is to understand and define the problem. Now, before we try out computational fluid dynamics, you must understand the underlying physics behind the problem. You should always check if CFD is feasible or not. You should also check if an analytical solution exists or not for your particular problem. If you have an analytical solution, there's not much reason to do CFD. It's almost always the case that no analytical solution exists, and this is why the advent of CFD in our community is so huge. You'll have to indeed get an idea of where the grid must be refined, that is, where we're placing grid points. Remember, we only know solutions where we have particular grid points. That's where the computer solves the problem. And of course, where it's not needed. The more grid points you add, the larger computer you'll need and faster computer you'll need to solve it in a reasonable time. Every grid point takes memory and processor to, of course, assess. We should always classify our flows in terms of laminar flow or turbulent flow, incompressible flow or compressible flow, etc., based on non-dimensional numbers. And different solvers will have different strengths. For example, particular CFD solvers will be designed either for compressible flow or incompressible flow, and would be inefficient or even impossible to find the physically correct solution in the other's case. Every time we do a CFD solution, we must validate and verify our results and use healthy skepticism to see if we found the correct solution. The first step, of course, is taking the geometry in the physical domain, which is shown in the lower left as a solid blue area, and transforming it into a computational domain. For example, the fluid might exist in the blue area, but we can only solve and find solutions at discrete points. Those discrete points are called the grid points or nodes of the domain, which are denoted in the lower right as the circles. The circles have a certain types of connectivity, which dictates how the equations are related to each other at each particular grid point in their discretized form. For example, we will know the solution at every particular grid point and how that's connected to other grid points with the CFD solver. This is what we call an unstructured grid, meaning that the grid ordering is not intuitive. It's not ordered by an implicit method. It's explicitly stated by the solver. Grid generation, indeed, is the most time-consuming part of CFD, at least for people. The most time-consuming part of CFD for, of course, computers is in the solver stage. Now, the grid points in their connectivity can be easily numbered in the billions or for large contemporary CFD problems. And indeed, there's a huge field of mathematics and engineers working to create the software to create the grids easily from particular geometries. Oddly, this is a fun exercise. On the right, you see one particular aircraft body with a particular unstructured triangular grid wrapped around it. Remember, the solver will either find the solution in each triangle or on the node which makes up each triangle. Given the grid, we should be able to find some kind of solution which is convergent numerically, hopefully, but this is not always found in practice given some boundary conditions in grid. Remember, the more grid points found in one of these grids, the more computer time you'll use, and computer time is directly correlated with money to run the computer. These simulations are very expensive and need specialized software to create the computational domains. Now, once the domain is created, the equations are discretized on it, and the solver, with appropriate boundary conditions, will try and find the numerical solution. This is an extremely complex mathematical problem, which is the subject of hundreds and easily thousands of researchers over many, many decades. And this numerical solution approaches and the solvers were developed even before the advent of digital computers, way back to the times, of course, of Leonhard Euler, who we discussed a history of in this very class. We often discuss the solvers themselves, and there's many different kinds, as a type of mathematical algorithm. And these algorithms, of course, are designed to find the solutions of the discretized equations. With the advent of, say, GPU computing and parallel computing that's using multiple processors to solve the problem, we call this class of solutions parallel computing or high-performance computing. These codes are often written in the language of C or Fortran. You will never find an efficient CFD code written in, say, MATLAB. They are written in low-level languages called C and Fortran, which are some of the two original languages of computer programming. In fact, Fortran was one of the first languages invented for, of course, engineers and mathematicians to program computers. It literally stands for Formula Translation Language. These are paired now with the message passing interface, which allows different processors and processors with different memory banks to communicate with each other on supercomputers today. Almost all CFD calculations today use either C or Fortran to program the code and the message passing interface for parallel computing with hundreds, if not tens of thousands of cores operating simultaneously. Now, the different solvers and algorithms have many famous names, which are too numerous to get into in this class. But for example, there's three very famous algorithms for incompressible flows called ACM, Simple, and Piezo, and these are available in almost all commercial codes like Fluent and Star. There's also a number of compressible flow algorithms like Piezo Compressible, which is Piezo with compressibility corrections essentially, the preconditioning techniques, and the famous FDV algorithm, which seamlessly handles subsonic and supersonic flows simultaneously in boundary layers and of course wakes and out in the free stream near shocks. Now, it's easy to try for a particular problem like an incompressible flow of compressible flow solver, and indeed that may vary and give you no solution, the wrong solution, or a solution might be found very, very slowly and never even achievable in your lifetime. So understanding the equations and the problem and the physics is essential for CFD, and also a deep knowledge of each particular solver. This choice, of course, will give you a financial savings through a reduced computational cost. Now, there's many choices of which equations to solve. If the equation models a fluid and you're solving it numerically, then indeed you're performing computational fluid dynamics. In some sense, you've already done some CFD in this very class by solving a few equations with, of course, a numerical method, like the compressible aerodynamics solver. That indeed is a type of CFD because we're solving fluid dynamics problems numerically. Often, turbulence modeling is required for the problems of interest. This is one of the most complicated subjects known in contemporary science and mathematics. There are many intelligent people working in this field without much success through their entire lives. There's often more unknowns for the equations than, of course, equations themselves. For example, the turbulence closure problem refers to the fact that there's more statistics of turbulence that we need to find to close the problem than there are fundamental physical equations, such as conservation of mass, momentum, and energy, and the gas law. This means since there's more terms that are unknown than equations, we need to model them. And this is the subject, of course, of turbulence modeling. To do this appropriately, we need to know the assumptions and when they're appropriate when we apply a turbulence model to a code. Applying one turbulence model to, say, a code, which is invalid for a particular flow, will give us a solution, but it can be completely wrong. And so in CFD, a complete understanding of turbulence modeling is really necessary to do simulations correctly. During the solver phase, we have to understand three important concepts, which can be viewed from general numerical methods classes. The first is, of course, is stability. Stability is the property where the solver, as it finds a numerical solution, causes the error to decay. The second is consistency, that the discretized form of the partial differential equation is indeed consistent. It's consistent with the original form. So that means if we solve the discretized form and let delta x and delta t go to 0, that we can recover the solution numerically of the continuum equation. Finally is convergence, and convergence is nothing but the property of having a solver which is both stable and consistent with the equations. On the right, you can see some examples of convergence criteria for different types of solvers for a CFD problem. On the y-axis is the error. On the x-axis is the iteration. As the solver progresses, it increases its iteration count, just like you did in numerical methods classes, but this is for different types of algorithms for CFD. For example, CG and ADI are two very famous solvers. In each case, you can see that the log of the error is decreasing quickly with increasing iteration count. The more quickly it decreases, the quicker the convergence will be obtained with the solver. These are the types of plots we look at in contemporary CFD to show convergence and low error in our numerical solutions. Observations of the computational grid and the solution being independent of the computational grid, along with visual inspection of the solution, will be required to see if we have a solution. After we find a solution and believe that it's of course converged, we can then post-process the results. Post-processing involves analysis, the examination, plotting, visualization, and extraction of the CFD solution. Indeed, the CFD solution is nothing but a bunch of numbers contained in a database, usually a very large one, of course, on a large computer. Typical databases can easily be in the terabytes or larger of disk space now. And of course, we need high-performance computing even to understand the results, and maybe even artificial intelligence through the big data movement, which is currently occurring in 2020. Visualization, of course, is viewing the results graphically like on the right, which is a figure from the APS-DFD of a jet in a crossflow. The black is the wall, and the lines and the contour lines are the Q criterion plotted within the jet in the crossflow. You can see the large, beautiful, turbulent vortices and structures forming in the crossflow jet. Extraction is the idea that we derive properties. For example, in this class, we derived the properties CL and CD from a solution which was analytical for the diamond airfoil. This is done automatically through more advanced algorithms in computational fluid dynamics to derive properties, say like Mach numbers or CL and CD. Usually CFD only gives us the field variables as the answer. For example, densities, velocities, pressure, and perhaps one other variable. From our algorithms, we would derive all other quantities like Mach number, lift, drag, etc. We often visualize solutions through graphs, and of course, experts through experience can observe non-physical results that are present in CFD to know if the run is valid or not. Post-processing is probably one of the most fun parts of CFD, which I think many students like initially. Here we have one particular view graph from NOAA of course, a hurricane system approaching the United States. Remember, we have to understand graph theory to do graphing, and there's many types of graph, and some are more qualitative than quantitative. Qualitative graphs are used, like on the right, to show physics. On the other hand, it's partly quantitative because we have a contour legend, which gives us a value of particular different values of, say, pressures. Graphs can be always used to convey physical concepts, but the best graphs are quantitative in nature, and we would like them to be compared with experimental measurements if possible to show additional validation. So, the post-processing phase could take our field variables and derive other quantities. One which you learned previously in aerodynamics or fluid dynamics is, of course, circulation. So remember, circulation is derived from the velocity vector as, of course, nabla cross u, which is defined as omega. So the omega could be the circulation as it's integrated over a surface, which we could define as capital gamma. This is all done automatically, of course, in the post-processing programs, or you could program your own if you have the numerical database from CFD. So remember, this is a crash course and overview of CFD. If these subjects seem interesting to you, of course you can go on and take CFD classes at the graduate school or introductory electives, which I sometimes teach here at the university. Remember, CFD consists of 3 basic steps: the pre-processing phase, which sets up the problem, the solver, which solves the discretized equations with appropriate boundary conditions on the grid, and the post-process, which of course finds derived quantities as part of the design and research process. No matter what you do in this course with analytical methods, experiments, or CFD, you must be skeptical. You always have to ask yourself, is this result correct? And what part of the process might introduce additional error? What are the uncertainties of the calculations? These are very difficult concepts to find, especially when you're working with deterministic equations of motion. You can have fun and, of course, explore any contemporary CFD solver. I recommend trying out some of the free versions of CFD online through maybe a summer or a couple months in your off time so that you can understand this beautiful field. And maybe then, if you're interested, you can go in and take courses and become an expert. Thank you very much for your time today. I'm Professor Steve Miller.